Okay, it's time to start. Welcome everybody to today's PALS. We're very happy to have Zoltán Vidnyánszky from Eötvös Loránd University, Budapest. He'll talk about constraint satisfaction problems in the descriptive context. Please, Zoltán.
Thank you very much, and thanks a lot for the invitation. So yeah, before I start, just feel free to interrupt me whenever if something is unclear. I will give an introduction basically to descriptive combinatorics first. So if you are familiar with the subject, well, apologies, this is not going to be super interesting. Then I will talk about CSPs for a short time, and then I will tell you what do we know about the CSP in this context. Okay, so all right. Should work. Yes. So first, descriptive combinatorics. So basically, okay. So the main notion which we will look at is chromatic numbers, but in our context, it's going to be slightly different, as you'll see. So well, everybody knows the classical notion of chromatic number, but I will just repeat it. So we have what is an n coloring of a graph. We have a graph and we have an n coloring, and an n coloring means that we want to associate colors to vertices so that adjacent connected vertices get different colors. So this is a proper n coloring, and the chromatic number is a minimal n for which such a coloring exists. Okay, so now in the Borel context, people always say that whatever we do, our whole area is just basically putting the word Borel after every second word in every definition. So this is what's going to happen. Well, first of all, for this to make sense is first of all we have to assume that the vertex set of the graph is a Borel space. So there is some sort of Borel structure in it. But if you don't like Borel sets, you should just think, or don't like in general topological spaces, you just think about the Euclidean space C, and there are Borel sets there. I mean, if you don't like Borel sets, then it's probably not a good sign for this talk, but otherwise it's going to be okay. And okay, so what about the coloring? So we first of all we assume that the vertex set of the graph is some nice standard Borel space, or even the Euclidean space, and then we require about the colorings that they are also Borel. Okay, and the graph that it's also Borel. Okay, so first of all, it's again not clear what do I mean by the graph being Borel. Now the graph can be identified with its edge set. And the edge set is a subset of this space, right? Of this product space, the vertices times the vertices. And since we have a Borel structure here, and we have a Borel structure here, we have a Borel structure on the product, and then we can say that the graph, the edge set of the graph is a Borel subset. So those are Borel graphs. And then about colorings, we'll also require that they should be Borel as maps. So a Borel n coloring of the graph is a Borel map such that adjacent vertices get different colors. And okay, so you ask, what does it mean to be, what is the meaning of a map being Borel? Well, we can consider on this n the trivial Borel structure as a discrete space. And then this map being Borel means that this is a Borel measurable map, or equivalently, in this case, it just means that a Borel n coloring is an n coloring where all the color classes are Borel. Okay. Okay, and then the Borel chromatic number of G is the minimal n for which such a coloring exists. Okay. And this is a notion which we want to investigate. I will tell you a bunch of examples, at least 2 examples, and they should be hopefully enlightening. Okay, so let's see. So the most classical example is the example of rotations. You can see it in basically every talk about the subject. So you You take the circle, and then you take an alpha, which is an irrational angle. This irrationality is important. And then you connect 2 points, x and y, if their angle is actually alpha. Okay. So this is the graph. And the first question, how does this graph look like? How does a connected component look like in this case? And if you think about it, well, x is connected to 2 things, and then y is connected again to 2 things, and then this new thing is also connected to 2 things, etc. And the point is, one interesting point is that you don't get back to the same place because alpha is irrational. This is partially why we chose it. So a connected component of this graph, so a connected component. Well, how does it look like? It looks like a bi-infinite line graph theoretically. Okay. And but there are a lot of connected components, right? So there are actually continuum many connected components. But still, graph theoretically, this graph is not super interesting. For example, its chromatic number, the normal chromatic number, which I denote by chi of g, is just 2, right? You just color red, blue, all these vertices, and it's not a super interesting object. One thing to notice also is that a connected component of this graph, so what can we say about it topologically? Well, it's actually a nice exercise that every connected component, or every orbit, if you wish, in this graph is dense in the circle. So observe also that this is going to be important in a second, that every connected component is a bi-infinite line, and dense, or forms a dense set. Okay, cool. And I claim that this example shows, this is why people like this example. This example shows that there is a dramatic difference already between the normal chromatic number and the Borel chromatic number. Here, the normal chromatic number is 2, and the claim which we are going to prove that the Borel chromatic number is actually greater than 2. So why is it the case? So let's show this. So assume for contradiction that there is a Borel 2 coloring, that the Borel chromatic number is actually, say, less than or equal to. So this means that S1 can be decomposed into 2 sets that are G independent. So BI are G independent. And they are Borel. As I mentioned, this is just equivalent to the existence of a 2 coloring. So GI, G independent Borel. Okay. Now, because of the Lebesgue density theorem, one of the sets is going to fill some interval pretty well. So because of the Lebesgue density theorem, there will be some interval I such that, say, the red, okay, so let's call these guys red and the other one blue. So the red points will fill this interval maybe up to 99% by the Lebesgue density theorem. And 99 will be a huge overkill. Okay. Now the observation is that, okay, great. So in this interval, almost everybody is red. Then it means that if I rotate this interval might be small, but I rotate this interval with alpha. Okay, so this is alpha. Then everybody else there must be blue, right? They are all connected. So again, 99% must be blue of these guys. Okay, and then I rotate it, and then 99% must be red. Okay, and then blue, red, etc. And then we use this observation about density that even if I look at 2 alpha, that's also irrational, and by the observation of density, there will be an odd rotated copy of this interval such that it intersects this original interval in at least half of the points. So again, by density argument of the connected components, and I use it for 2 alpha components, some odd rotated copy. So oddly, I hope that makes sense. So odd rotated copy intersects I in at least half of the size, but that's bad, right? Because 99% here has to be Borel, sorry, 99% here has to be blue, and 99% there has to be red, so that's a contradiction. Okay. Okay, good. And the other claim is, okay, now we have separated these 2 chromatic numbers. And the other claim is, which is, I think, also nice, is that actually, because maybe after this you might think that, okay, you cannot do anything in a Borel manner, so maybe it's not an interesting notion. But actually you can 3-color in a Borel manner. And how do you do that? That's a very cute argument, and you will see it again. So basically you pick an interval which is smaller than alpha, and then you color it green, okay? So this is going to be the interval. You decide that it's green, and every other point, again, by this density argument, will jump into this interval at some rotated copy. Maybe not now, but it will jump here. And then I color X according to how the parity of the jump. So I count how many jumps do I need. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I color it red, and then I color this blue, then I color it red, blue, etc. Okay. So basically what's going to happen is that not only these guys around here are red, these guys around are blue. And this is it, right? So every 2 adjacent points, like here in the green one, there are no 2 adjacent points. And because of this parity coloring, there are no blue or red adjacent points either. So this is a proper 3 coloring. Okay, so we have separated it and we have determined the Borel chromatic number of this G, and this is actually 3. Okay. So this is a nice example, but somehow I like the next example more, because in this example, sort of, or maybe if you encounter it first, you see that your impression might be that this Borel thing is just weird because it should be a 2 coloring. The right intuition is that there are these bi-infinite lines, and in some sense, every point thinks that they are special. So there are no leaders. You cannot pick a reference point, really. And to do this 2 coloring, you should do something like that. And this is not possible in a Borel manner. I mean, in other words, you could say that there is this Vitali equivalence relation, if you know what that means, and you want to have a Borel set which intersects somehow in every equivalence class in a single point, and that is not possible. Somehow this is some sort of intuition here. You cannot break symmetry in a Borel manner. Okay, and my favorite example is the following. This graph is called the shift. And the graph is on the infinite subsets of the natural numbers, the inherited topology from the product topology on n to the n. So again, this is a nice Borel space. And the shift map is defined as follows. I have an infinite set, and then I erase the minimal element of this infinite set. Okay, and then I again connect 2 points if one is the shift of the other or the other way around. Okay, let's draw a connected component. So how does a connected component here look like? I will now draw a directed graph according to shift, but this is an undirected, a normal graph by definition. It will not matter. It will matter only maybe for the picture. So, okay, so let's see, how does it look like? So there are points which start with 0 and then, okay, continue, whatever. And then you erase them, maybe 20, 211, and then you erase the first element, you get this to 211, and then you blah, 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 and then you go to this 211, sorry, and etc. So, and then, but you can also get to this point from other points, right? So you can get here from, say, 187, 211, or even maybe 2. So it will look something like this. Okay, some kind of tree. I mean, I imagine it going into some sort of spine. This is how it looks like. Okay, this is a connected component of this graph. And okay, so what about this chromatic number? Well, if you believe that a connected component looks like this, then again, it's acyclic. So the normal chromatic number of this GS is again 2. What about the Borel chromatic number? The Borel chromatic number happens to be infinite. This is an observation by Kekrisoletsky and Todorchevich. Let's prove that. And I like this example because I think Borel chromatic numbers very often behave better than normal chromatic numbers. And in this case, I even have an argument for that. Okay. And this theorem, this statement is based on a very nice theorem, which I think is not sufficiently popular. And this is called the Galvin-Prikry theorem. So what is that? So the normal Ramsey theorem, the infinite Ramsey theorem, says the following, that if you color the pairs of natural numbers, then you can find an infinite subset such that all pairs are to 2 colors such that all pairs are monochromatic, okay? Or even finitely many colors, then you can find an infinite subset that all pairs are monochromatic, right? This is the normal Ramsey theorem. But also it's typically an exercise in these combinatorics classes that instead of coloring pairs, you can also color triplets, right? So this is a hypergraph Ramsey if you wish. So triplets or even k-tuples you can color, and then you can find an infinite subset such that all k-tuples are monochromatic. And if you are really greedy, you want to color infinite tuples of natural numbers, which is this space, right? So you want to color this space with finitely many colors, and then you want to say that there will be an infinite set such that all infinite subsets are monochromatic. Okay? But this is false. This statement is just false. However, if you instead require that the coloring is nice, it's Borel, and every reasonable coloring, or most of the reasonable colorings just happen to be Borel, then this is a theorem, and this is a highly non-trivial theorem actually of Galvin and Prikry. It says that if you have a Borel finite coloring of infinite subsets of the natural numbers, then there is an infinite subset such that all further infinite subsets of A have the same color. Okay, and then this statement is sort of easy now, right? Because so what does that mean? Assume that this graph GS had a finite coloring with k colors, then I can find an infinite subset which is completely monochromatic, but then in particular A and the shift of A are of course in this set, right? These are all subsets of A, and they have the same color. They are connected according to the shift. So this cannot be a proper. Okay. So that is also, I think this is a cool example, and there is a very nice property of this graph, which I can even sketch the proof of, because I mean I don't know, I like the statement. So so you look at the subgraphs of Borel subgraphs of GS, and then you want to determine the Borel chromatic number of these things. And it turns out that the Borel chromatic number is 1 2, 3, or infinity. So there are no dot dots here. So there is a jump. It's either 1, 2, or 3, or infinity. Kekrys and Todorchevich called this theorem the 1, 2, 3 infinity theorem. So why is this the case? So let me sketch this. Let me sketch this proof. I think it's pretty nice. So again, we go back to this picture of the graph. And what do we have to prove? We have to prove that for this statement, we have to prove that once you have a finite coloring of the graph, then automatically you have a 3 coloring. And this is done as follows. So you look at the connected, you have to believe that everything what I say here is Borel, but it's Borel. I mean, the intuition is that whatever is constructive, you don't have to pick points. It's always going to be Borel. So this is the case here. So you look at a connected component and assume that you have a finite coloring with 7,000 colors. And I look at the point and I look forward. This is sort of the forward orbit. So I look at these iterates. So since there are infinitely many of them, one color is going to appear infinitely often. I just pick the color which appears infinitely often, the minimal one according to some ordering. So it looks something like this. Okay, and then what I do is for every other point, okay, so then I just look at this orange color. I decide that this is my favorite on this connected component. And for any other point, like I pick a point here and I look at its iterates, sooner or later in this connected component, I will hit an orange point. And then I just do the same as what we did in the case of S1. I just count how many steps do I have to take, okay, to hit this orange point, and I color according to the parity. So I color this blue, color this red, color this blue again, red. So orange plus parity coloring, that's 3 colors, right? So we have just shown that once you have a finite coloring, you automatically have a 3 coloring as well. Okay, so we have this theorem. All right, so these are the 2 examples, and sort of, okay, so you can say there are these nice Borel graphs or whatever, and there are these theorems, but why do you care? Why do you care at all about these Borel graphs to begin with? And so one reason for which we care is equidecompositions. So it turns out that when you want to do this kind of equidecompositions like circle squaring, you have to find a perfect matching in some very nice Borel graph. And if you manage to find, say, a Borel perfect matching in that graph, which is sort of maybe you can think of as a generalized coloring problem, then you can do a perfect matching with nice pieces, with Borel pieces. And this is what has been achieved by Grabowski, Mate, and Picurco with measurable pieces, and Marx and Unger with Borel's pieces later on. And you can even see this picture that you can square the circles with relatively nice pieces. Okay, so this is one reason for which people care about, in general, solving graph theoretic problems in nice manner on nice graphs, so in Borel manner on Borel graphs. Another thing for which I care about is that you can formulate complexity-related questions. So after this theorem, or after this investigation of shift graph and this theorem, this 1, 2, 3 infinity theorem, people just asked, okay, can we understand the subgraphs of the shift for which there is a 3 coloring? Is there a characterization or something like that in this situation? Can we decide the chromatic number in some sense? And the descriptive context is really nice because we can make sense of complexity there. So, okay, so what do I mean? So so the question is it possible to decide the 3 colorability of say, a Borel graph? Okay, and And this can be formalized, okay, and somehow from the finitary world, you might conjecture that 3 coloring is actually very hard to decide. And you can even formulate it in the descriptive context. You can do the following. You can ask you can ask the following question: if you have a bunch of Borel graphs, so each section here a Borel graph, so these are X, and you have Gx, a Borel graph, and then you can, okay, and this assume that this is sort of a Borel set altogether, and then you can ask about the collection of those X's for which Gx has a Borel, say, 3 coloring. Okay, so for any Borel set on the plane or any Borel collection of Borel graphs, I can ask how complicated is this set. Okay, and in descriptive set theory, we can make, and I guess in other areas of logic, we can make sense of this complexity question. And then if you write down the definition of these X's, you get the following statement. So you get that, okay, so what does it mean that you have a Borel 3 coloring? So it means that there exists a 3 coloring, okay, so the existential quantifier coloring, and then you want to say that there exists, okay, maybe a C, such that C is a 3. To write this down, what do you need to write? 3 coloring is that for every X and Y, blah, 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 happens that for every X and Y, if they are connected, then their color is different. So if you look at this statement, this is an existential and a universal quantifier. And these kind of sets, which can be defined with using those and over the reals, so these are over the reals, these are called sigma 1, 2 sets. So by definition, sort of, it's a sigma 1, 2 set, and you can introduce the notion of most complicated sigma 1, 2 set. And turns out that such sets exist, and you can say whether a set is sigma 1, 2 hard, and this again says that it is sort of more complicated than the most complicated sigma 1, 2 set. Okay, and then there is like a somewhat there is a nice analogy with these hardness statements from computational complexity or hierarchies. And then it turns out that so we proved with Stevo Todorcevic that Borel n-colorability is sigma 1, 2 hard. It means that there exists such a Borel set such that this indices or these X's, these parameters for which the corresponding set corresponding graph has a 3 coloring is sigma 1, 2 hard. In fact, it's going to be sigma 1, 2 complete. So this is sort of the optimal statement. And this, in some sense, says that you won't be able to understand, won't be able to have a nice description of when does a graph, a Borel graph has a Borel 3 coloring, because any description is going to be as complicated as sort of the definition, right? So sigma 1, 2 hard implies in particular that it's not going to be something simpler, and it says that okay, you don't know what to do here. But somehow this is what we expect, and in particular, it turns out that for Borel subgraphs of the shift, it's already hard to decide whether their Borel chromatic number is less than or equal than 3. So it also says that already there is this gap, right? So deciding between whether a graph has infinite Borel chromatic number or 3, it's already sigma 1, 2 hard thing. Okay. Okay, and what about 2 coloring? And as you would expect, I don't know if you would expect that or not, but somehow 2 coloring seems to be easy. And indeed, Borel 2 coloring is just pi 1, 1, so you can describe this with a single universal quantifier. So there is a distinction between n coloring and 2 coloring, and this can be formalized, and this can be proved that these classes are different. So I think it's a pretty interesting situation. Okay. So this is about descriptive combinatorics and complexity, and this suggests the CSP direction. Okay, so what is the CSP direction? I mean, let me quickly recall this finitary situation. So, I'm sorry if you know all this. So yeah, maybe I should ask, are there any questions?
So are there any other typical sigma 1-2 hard or sigma 1-2 complete problems in Borel complexity besides what you have here?
Well, so I will mention a few in the CSP
Okay.
direction, but there are also sets which come up, say, naturally on analysis. So, for example, if you take the collection of those compact sets, which are in the three-dimensional space, which are arc-wise connected, so then it's which are not arc-wise connected. These are again sigma 1-2 R. So there are a bunch of examples in Kekris's book. I mean, very often if you write down a set which doesn't have like a simple characterization, then you can prove that it's sigma 1-2 hard if it's sigma 1-2 itself. Yeah, I think these are, and yeah, I don't know if I'm aware of like much more natural examples, but there are things like this.
Thank you.
Okay, so I continue with the CSPs. The situation there is the following: we have a finite relational structure H, and now everything is finite. So we have another finite structure G, and then we ask whether G admits a homomorphism to H. And the classical examples is, well, graph n-coloring, because having an n-coloring is just a homomorphism to a complete graph on n vertices. Okay, so graph n-coloring is a CSP. Graph homomorphism to some fixed graph is a CSP. More interesting is the systems of linear equations over some finite field, which I will denote by 3ln2, is also a CSP. You can encode it in some homomorphism problem. It's not completely clear how to do that, but it's possible. So first of all, you replace every equation with using dummy variables. You can assume that every equation has at most 3 variables, and then you introduce this structure, which has which sort of encodes what is the sum of these variables, and you just easily check that a homomorphism to this encodes a solution to some system of linear equations, and then you can of course do it for finite fields over some larger characteristic set. Okay, and of course NSAT, Hornsat, these classical examples are also CSPs. And turns out that CSPs fall into 2 categories. Some of them are easy. They are polynomial, sometimes solvable, like 2SAT, and some of them are NP hard, like NSAT, similarly for 2 coloring and N coloring. And the first, one of the first results was by Hell-Neshatri, who actually characterized for which graphs H coloring is polynomial time solvable. This is precisely when H is bipartite, and otherwise when H is non-bipartite, then H coloring is NP complete. Well, what about these systems of linear equations? We can solve them polynomial time using Gaussian elimination. Okay. So based on this table, maybe not on this table, but based on some table which is similar to this, Fader and Vardy conjectured the CSP dichotomy, which is that any CSP is either polynomial time solvable or NP or NP harder. And in this case, it's going to be NP complete, of course. So, all right. And then Bulatov, Jevons, and Krokhin isolated some property, which I will call star, for which I will just say something about it later on, such that if this is an algebraic property of the structure H, such that if this fails, then the homomorphism problem is NP hard. And actually, they conjectured that if this holds, then the homomorphism problem is in P. So this should be, of course, H home. Okay, and then the main result is by Bulatov and Shuk, who has shown that actually this is true, that if this algebraic condition is satisfied for H, then the H homomorphism problem is polynomial time solvable, and together with the above result, this verifies the conjecture. Okay, and I mean, just to say a couple, just a slide about what is this algebraic condition. A polymorphism of H is a homomorphism from Hn to H, and turns out that these characterize the hardness. So roughly speaking, this star says that H has no non-trivial higher dimensional symmetry or polymorphism. Okay, and turns out that if it has one, then it's easy to solve, and if it doesn't, then it's hard to solve this problem. Okay, so going back to Borel things, to Borel CSPs, it was actually Thornton who suggested, Riley Thornton, who suggested that the systematic investigation of CSPs in the Borel context. I was aware of Hellner-Shetril result, but at that point I was not aware about the CSP dichotomy. But of course, you can Borelize everything, right? So you can look at Borel structures where the structure itself, again, is some subspace of some product, and then you have to require that the homomorphism is a Borel thing, but we still keep the target fixed, as in the case of N coloring. Again, the target was like some finite thing, and then you look at whether there is a Borel homomorphism from this Borel structure. And so this is the thing. So G and the homomorphism is required to be Borel. So this is just a generalization of the Borel and coloring problem. Okay. And actually, Thornton managed to show that if this star fails, so this algebraic condition doesn't hold, that there are no non-trivial symmetries, then the Borel homomorphism problem is sigma 1 too hard. Okay. So this means that, okay, so if this is the big picture of all CSPs, then in the finite world, there are two kinds of CSPs. One of them, okay, one kind is the NP, is the NP hard ones. So for which this star, I mean, of course, NP and P could be the same, but let me just pretend that they are not for the sake of the picture. So for these ones, star fails, and for these ones, star holds, and they are polynomial time solvable. Okay, so this is in the finite world, and then what Thornton proved that if we look at this blob in the Borel context, so this then these guys here, all these are sigma 1 too hard. Okay, and this is perhaps not surprising if you are familiar with this Bulatov-Jevons-Krokhin thing, because what happens there is that there is a very, very concrete reduction between problems, some sort of gadget reduction. And then what happens is that every problem which doesn't satisfy this property can encode this recoloring. So it should be at least that hard. And with some work, there are some non-trivial steps here. You can pull it to the Borel context, and again, every homomorphism problem in the Borel context happens to be if it doesn't satisfy this property, then it happens to be sigma 1 too hard as well. And we know that somewhere here there is two coloring, which is again easy. So there are somewhere here the pi 1 1 problems. And my Jugendtraum, my childhood or adolescent dream was that the two hierarchies will actually match. So the problems which are hard in the Borel context are going to be exactly the ones which are hard in the classical context, and everything else is going to be, so the easy ones are going to be pi1,1, and this is going to be actually some evidence again that this is not just a fake split but the right split. And because these classes sigma 1, 2 and pi1,1, they do not coincide in the Borel case. We can prove that. So this would be sort of very nice. Of course, there would be absolutely no implication, right? Formal implication. There are no formal implications between the finite and infinite hardness questions, but still it would have been a very nice situation. So we worked quite some time on trying to show that this is the case, that everybody here is actually pi1,1. In particular, there are these examples of systems of linear equations, which would have been a very reasonable class to attack and to understand whether the Borel complexity problem there is easy. And of course, it turns out that it's not. So already in the Borel case, the separation is somewhere some different place. Sorry. So it's at some different place. So hard problems are going to be over there. So systems of linear equations are already very hard to solve in the Borel context. This sort of means something like there is no, because Borel, even somewhat formally, you can say that Borel is roughly the same as some sort of having a Borel algorithm is some sort of parallelizable thing. So you can doing something in a Borel way means that you don't have sort of leaders. You do something in parallel, and it says in some sense that there is no version of Gaussian elimination in that context. In Gaussian elimination, somehow you have to pick some sort of leader in some sense. Okay, but this is only an intuition. The formal statement, of course, is that this Borel 3 is a sigma 1, 2 hard problem. Okay, and so then of course the question is where is the dividing line in the Borel context? And then maybe the adulthood dream was that actually it's going to be the so-called bounded widths. So somehow here you have bounded widths, and hopefully this is what coincides. And I thought that then it should be not hard. But Honza came up with Honza Grebik came up with some examples which are very much bounded widths and very simple seemingly, and we couldn't solve that either. And the story is that, I mean, this paper is already on arXiv, so I said that we give it one last push, and then if we cannot solve it, then this is going to be an open question. But this example, which we suggested, can be actually solved. So we showed something like this. So maybe it seems that it will require a significant amount of work, but there is some progress towards this conjecture. So I still conjecture this, even formulated this, yes, that the Borel homomorphism problem is pi1,1 if and only if H is bounded widths. And one question is why? I mean, why is it the case that this is the place where the Borel separation happens? And I don't quite know. I mean, it would be reasonable to guess that since in the finite context, polymorphisms play sort of a central, polymorphisms play a central role, it would be similar in the Borel context, but I'm not quite sure how to build this theory of Borel polymorphisms even. So I guess this is another problem. So I don't know what is the right notion of Borel polymorphisms. My guess is that it's going to be just very simply adopted, and instead of h to the n, we look at h to the natural numbers. This is again a nice Borel space, and we look at maps like this, but I'm not quite sure what would be the right statements here. There are some observations which sort of push us into this direction. And yeah, so the ultimate goal would be that there is a third equivalence saying that Borel homomorphism problem is pi11 if and only if H is bounded with, if and only if H has no trivial Borel polymorphisms, whatever they are. Okay, yeah, I think I'm a bit too early, but this is basically, yeah, all what I want to say.
Thanks a lot.